In this video, we want to look at vector fields and radial fields in R3 space. Everything that we've developed so far, working with vector fields and radial fields in 1 and 2 dimensions, is also valid in R3 space. And while we can and do work with these fields in lower dimensions, it's really in the R3 space that vector fields show off their power and functionality. So let's let f, g, and h be functions defined in a region D of my R3 space, and there's a vector field in R3 that is a function capital F that assigns to each point in my region D a vector with components f of xyz, g of xyz, and h of xyz. The vector field in R3 can be written as a capital F with an arrow over it of xyz, or a boldface capital F of xyz, which is given by the component form of components f of xyz, g of xyz, h of xyz, or we can write it in vector component form as f of xyz in the I hat direction, plus g of xyz in the j hat direction, plus h of xyz in the k hat direction. A vector field of f is equal to the components f, g, h is continuous or differentiable on a region D of R3 space if f, g, and h are each continuous or differentiable on D respectively. Now, of particular importance are going to be the radial vector fields, and these have a specific characteristic in that my radial vector field of f of xy is equal to the vector r over the magnitude of r raised to the p power, which is equal to my vector xy over the magnitude of r raised to the p power, where p is a real number. Now, sketching vector fields in R3 can be a little bit challenging. So we're going to start by evaluating the behavior of the vector field with respect to the x and y components in the xy plane, and then consider what the z component is going to do. So we'll consider asking questions like, do the x and y components indicate a radial field? Is there a rotation in this field, and if so, what direction does it lie in? Do the x and y vector components increase or decrease in length as I move away from or toward the origin? Does the z vector component increase or decrease in length as I move away from the xy plane? So let's work an example. I want to sketch a few representative vectors in the vector field given by f is equal to the components x, y, z. I'm starting with a three-dimensional coordinate system with the positive x, y, and z axes represented. And for all points where z is equal to 0, this particular vector function is going to give me this particular vector field in xy space will give me a radial field with vectors that increase in length as I move away from the origin. So in the xy plane, I'm going to sketch some representative vectors indicating that increase in length as I move away from the origin. And now I think about my z component, which also grows longer as I move away from my xy plane, and they all point directly away from the origin, so that a few vector examples here will be vectors that point off into space away from the origin of my three-dimensional system, with vector lengths growing longer the further I get away from my origin. I'm going to show you a more detailed sketch of this particular vector field. When I do this in a full 3 dimensions, I get a lot of different vectors pointing directly outward away from the origin. They are all radially outward, which means they all point away from one central source point, which in this case is the origin. Now I want to talk about gradient fields and potential functions, because this also allows me to generate vector fields using a differentiable scalar valued function, which I'll call phi, and we take the gradient of this scalar valued function phi and let my vector field f equal the gradient of this scalar valued function. When we define this vector field using this gradient of this scalar valued function, we have something called a gradient field. The scalar valued function phi is called my potential function. Now, if I have a potential function phi that is differentiable on a region of R in R2 space and a surface given by z is equal to phi of xy, which we can represent as a set of level curves in the xy plane, then at every point AB on each level curve, the gradient del phi of AB, as given by the vector with components phi sub x of AB and phi sub y of AB, will be orthogonal to my level curve. This means that the vectors in my vector field F given by del phi point in a direction that is always orthogonal to the level curves of phi. And we can extend these gradient field and potential functions into R3 very simply. We have a potential function phi differentiable on a region D in R3 space this time, and we have a surface given by z is equal to phi of xyz. Then I define my vector field F is equal to del of phi, which is equal to a vector with components phi sub x, phi sub y, phi sub z. This is a vector that points in a direction that is always orthogonal to level surfaces of phi. If I let z equal phi of xy and w equal phi of xyz, and these are differentiable functions in the regions of R2 and R3 respectively, then the vector field F given by del phi is a gradient field, and the function phi is the potential function for F in both of those spaces. So let's work an example. I want to find the gradient field F equal to del phi for the potential function phi of xy is equal to 2 times xy, provided the absolute value of x is less than or equal to 2 and the absolute value of y is less than or equal to 2. And then I want to sketch a few of the level curves of phi and some example vectors for my vector field. So my vector field F is given by del phi, which is equal to the vector with components 2y, 2x. When I construct my level curves for this function phi, my level curves look like two sets of hyperbolic level curves. One set of hyperbolic curves exists in Q1 and Q3. The other set exists in Q2 and Q4, respectively. Now I'm going to construct my sample vector curves. Remember that my vectors are always going to be perpendicular to my level curves. So I simply draw several of those along my Q1 hyperbolic level curves. And I'm going to use symmetry to recognize that in Q3, my vectors will just simply be reflected across the origin. Then when I look in my Q2 and Q4 quadrants, I notice that my vectors point slightly differently from that, still orthogonal to my hyperbolic level curves. But these vectors point inward more toward the center of the graph than outward. Let's work another example. I want to find the gradient field F is equal to del phi when my potential function phi of xyz is given by the natural log of the quantity 1 plus x squared plus y squared plus z squared. So the first thing I do is take the gradient of phi. F is the gradient of phi, which is equal to the vector with components 2x over the quantity 1 plus x squared plus y squared plus z squared, 2y over the quantity 1 plus x squared plus y squared plus z squared, and 2z over the quantity 1 plus x squared plus y squared plus z squared. And I'm going to look at this and notice that this might be easier to express in terms of spherical components. This becomes 2 times the vector r over 1 plus the magnitude of r squared. Now I want to talk about something called equipotential curves and surfaces. When I work with potential functions that exist in R2 space, my level curves associated with phi of xy are called equipotential curves. These are curves that represent sets of points where the potential function has a constant value. That just means that all along that equipotential curve, my potential function has the same value. If I'm working in R3 space, I work with level surfaces that are associated with phi of xyz, and these are called equipotential surfaces. These are the surfaces where the potential function has a constant value over the entire surface. In either case, R2 or R3 space, my vector field is represented by continuous flow curves or streamlines that are always orthogonal to equipotential curves or surfaces at all points. I want to show you an example of this because this is slightly different than what we've been doing. I want to take a potential function phi of xy, which is equal to x plus y squared, and the equipotential curves that you see in my sketch, which show a set of sideways parabolas that open to the left as my equipotential curves in the xy plane. I want to find the associated gradient field f of del phi, and I want to show that the vector field is orthogonal to the equipotential curve at the point 1, 1 and at all points xy. And then I'm going to sketch some flow curves for f that are everywhere orthogonal to the equipotential curves. The first thing I want to do is find the associated gradient field f is equal to del phi. This tells me that del phi and f is equal to the vector with components 1, 2y, which we know is orthogonal to our level curves. Now I want to show that the vector field is orthogonal to the equipotential curve at the point 1, 1 and at all points xy. At the point 1, 1, my tangent vector is parallel to the vector with components negative phi sub y of 1, 1 and phi sub x of 1, 1, which is equal to the vector with components negative 2, 1. This is normal to my vector field f, which is equal to 1, 2. And this is true for all points xy because I will always have a component of 1 and a component of 2y in my vector field. Now I want to sketch my flow curve. In this case, I'm going to have vectors that are perpendicular to a level curve that may be, as they extend out further and further, continue in a straight line to be perpendicular, or there may be flow curves closer in that have to bend as they cross through my equipotential surfaces in order to remain perpendicular. These are rough sketches, so I want to show you a more well-constructed set of flow curves for this exact situation. Here is a flow curve for this particular potential function. I'm going to reproduce the curves that I generated on my earlier sketch here so that you can see that we are fairly accurate given our ability to eyeball some of this. So now you get to try it. I want you to pause the video, and given the potential function phi of xy is equal to x squared plus 2y squared, and the following equipotential curves, which resemble a set of elliptical level curves centered at the origin with a major axis along the x-axis, I want you to complete parts A through C. When you're ready, restart the video to check your understanding. In A, you want to find the associated gradient field f is equal to del phi. In B, you want to show that the vector field is orthogonal to the equipotential curve at the point 1, 1 and at all points xy. And in C, you want to sketch two flow curves for f that are everywhere orthogonal to the equipotential curves. The first thing we do is find the gradient of phi. The gradient of phi gives me my vector field f, which is equal to a vector with components 2x, 4y. Now I want to show that the vector field is orthogonal to the equipotential curve at the point 1, 1 and all points xy. At the point 1, 1, the tangent vector is parallel to a vector with components negative phi sub y 1, 1 and phi sub x 1, 1. This is equal to a vector with components negative 4y and 2x. This is normal to the gradient field at the point 1, 1 and all points xy. Now I want to sketch two flow curves for f that are everywhere orthogonal to my equipotential curves. I'm going to actually graph 3. As I move further out along my equipotential curves, the vector flow begins to behave more like a straight line, remaining orthogonal across all curves. But when I get closer in toward the origin, you'll notice that my flow curve has to bend slightly in order to maintain an orientation that is orthogonal at all equipotential lines. I'm going to plot the actual vector field and show that the lines that I sketched into my rough draft look very much like what these flow lines would give me. So this is how we can work in both R2 and R3 space and use equipotential fields and potential functions to make our work in constructing vector fields somewhat easier to perform. Be sure and let me know if you have any questions.